Okay, so we are going to study finite difference first in the context of parabolic equations. So probably the easiest to study over here. Actually, finite difference work extremely well for parabolic equations, and less so for hyperbolic equations. So in all the three methods, finite difference, finite volume, and finite element, we are going to be asking these questions in order. First of all, how to do it, right? How do we approximate the partial differential equation? Particularly, how do we approximate the derivatives in it using arithmetic, which means computations without derivatives? How do we get rid of the derivatives, right? And the two is that by doing this, how much error have we committed? And three, that is not immediately obvious, is that how does this approximation error affect the solution? Right, so we know there is a certain difference between the actual derivative and our approximate derivative, but how much does it matter? Maybe it doesn't matter much. Maybe it makes my entire solution wrong, right? So these are the three questions that is actually very important for any numerical method, not just the ones we study over here. Okay. So first of all, how do we approximate a derivative? And let's start with this. The simple heat equation. As if you have done the self-assessment project, or at least have attempted it, we have actually given you the answer here, right? So if we have a uniform grid of 0, 1, and the delta x, 2 delta x, etc., where 1 is equal to, let's say, n times delta x. So here, delta x is equal to 1 over n, right? So we have n plus 1 grid points. Well, because we start from 0, right? So the indexing is something that I see a lot of potential mistakes in your projects and programming assignments. In finite difference, we have n plus 1 grid points, including the boundaries. Or if you choose to not include the boundaries, we only have n minus 1 grid points, right? So that can be a little bit tricky. So, and we only care about the solutions at the grid points. So W at, let's say, I times delta x, we just use is represented as W subscript I. Okay, so that's basically that's the only numbers we approximate, we store in the computer, and the only numbers we solve for in finite difference. All the other points we can interpolate, right? We can use whatever interpolation you know how to use, or just use MATLAB's own interpolation function. You don't even have to know how it works to interpolate. So if we only care about these WI's, then we also would only care about the derivative of W at these grid points. So basically, the derivative of Wi to t is actually equal to the partial derivative of t of W at x equal to I delta x, right? Because this is a classical example of taking derivative of a function while holding the other variable constant. The other variable is x, right? Because we are looking at a grid point that doesn't move. The derivative of the solution on this grid point is, of course, the partial derivative of that function. So that is equal to, well, kappa times the second order derivative at x equal to the same point. However, we don't know what it is, because by definition, the second order derivative depends on actually not just on the point itself, but on the value of the function at points nearby, actually infinitesimally nearby. While we are using finite difference, so the only points, the nearest points we know is actually I minus 1 times x and I plus 1 times x. They are finite difference away, right? So we don't know the second order derivative. So how do we approximate it? Well, the idea comes from, again, an intuition of what second order derivatives are. So what is second order derivative? I mean, when I say second order derivative, how is there any way you visualize what it is? If you draw a function, right, the value of the function is how high that curve is at particular point, right? So that's how I visualize the value of a function. How about the first order derivative? Yeah, it's slope, right? The first order derivative is what the slope is, right? So if it's positive, it's sloped upwards. I mean, upwards for you is that way. And if it's negative, it's sloped downwards. How about second order derivative? Yes, is the function concave or convex, right? So if the second order derivative is positive, the function looks like a smile. And if the second order derivative is negative, it looks like a frown. So that's how the second order derivative looks like. Okay, so now if you think of that, how do you, if I only know the value of the function here and here and here, if the function looks like that, is it more likely to be a smile or a frown? More like a smile, right? If you connect them, the function looks like a smile. So we can actually get an intuitive approximation of what the second order derivative is by just looking at the neighboring points. And in particular, if I can describe a smile as being, well, the average of the two nearby points being greater than the value of the point itself, right? So if I take an average, I'm just connecting the 2 points with the line and look at the middle of this line. So that's the average. If it's higher than the value of the point itself, it's more likely to be a smile. If it's lower than the point itself, then I know the second order derivative is more likely to be negative. Okay, so that's the intuition behind approximating the second order derivative using the average. Well, let's say at I delta x as the average between these two nearby points. So wi minus 1 plus wi plus 1 over 2 minus wi. Now, this gives well, I should say not just the approximate to, but the proportional to, right? But then, what proportionality constant should I give to it? Yeah, it has to do with spacing, right? But exactly how do we do that analysis? The analysis, well, there are two ways to get to the proportionality constant, but let's use the most general way. That's actually starting to be our introduction to the Taylor series analysis.